my lover. Don't take it so slow.
So let's bridge that. So remember that I said the norm, which is denoted by a P, right, in those fancy signs, means, this means the length of the largest subinterval, okay? The largest subinterval that we consider or compute. So if we were to do the limit as this norm, as the length of the largest subinterval goes to 0, as it tends to 0, so as it becomes really, really tiny, and we're basically forcing all of our subintervals to be tinier and tinier, really minuscule. So if we're taking the limit of that, of our Riemann sum, this is going to approach some limit, okay? And this limit actually turns out to be, this limit is going to be the definite integral, what we're going to call the definite integral of f of x over the interval a, b, okay? And this is going to be denoted by an integral sign. This is a fancy like extended s thing. And then a to b, that's our x limits, all right? And then f of x and dx, okay? So this is our definite integral. So let me show you. So the process of taking this is called integration, all right? Integration, and then we have our integral sign, a to b, f of x, and our dx. Okay, so these things, a and b, those are called our limits of integration, okay? The f of x itself, integration, so f of x is called the integrand, okay? So that's what's inside, basically. So what do you integrate? That's called your integrand, all right? The dx, that's just our differential, it's called. Okay, differential means how much you're changing. That represents little changes in the x direction. Okay, so little changes in your x value. All right, so and another note is that any variable could be used, not just x. You could have a t in there just as well, or like f of u du or something like that. Okay, it's not just restricted to an x. Okay, so now what we'll deal with is we're going to interpret the integral. So the interpretation as a signed area. Signed, not signed like an autograph, but sign as in positive or negative, okay, as signed area. So let's look at a graph, okay? So let's say here's our x and here's our y axes. So we have something like this that goes above and then it drops down below and goes back up, okay? So this is our f of x. So let's say we're integrating from here's point A, and here's the x value of b, okay? So if we're trying to take the integral, so this is a to b of f of x dx. So that's how we denote it. This is basically equal to the area. It's commonly known as the area under the curve, okay? So by under the curve, I remember when I was learning integration, I was so confused by this because I thought it meant under as in like everything under, like going down to the deep abyss of nowhereness. But it actually doesn't mean that. It doesn't mean all the way under. It means basically this under means the distance between, so between, under means between the curve itself, the curve, and the x-axis. Okay, so that makes things a whole lot simpler. That just means that, so here's the curve for this part, here's the curve, here's the x-axis, curve, x-axis. So this area under here, okay, and then as we go negative, it doesn't go below or anything like that. It's not that. But it just means here's the curve and here's the x-axis. So basically this part, okay? So that makes things a whole lot simpler, right? So this is the area we're trying to find. And what I mean by signed area is that when the curve is above the x-axis, so like it is on this part here, all the way up to this point, when it's above, then that means that our area is positive, okay? So then we have a positive area. That's how we consider it. But when it falls below, when the curve is below, down here, below the x-axis, that means even though the area technically still has to be positive, but we consider it a negative value. We're going to subtract it away from the total area. So what that means is that our a to b of f of x dx is basically composed of the area above the x-axis, so area above, and then we're going to just have the area below. We're going to compute that as a positive value, but we're just going to subtract it from the total, okay, because it falls below. So let's see an example of this in action. So let's say we want to compute the integral from 0 to 5 of 3 minus x and then dx. Okay, so here we see, here are the limits of integration. We're integrating from 0 to 5. Okay, and then this is our integrand. This is like our f of x. Okay, so now what we want to do is actually graph this function. So we're going to graph 3 minus x is equal to our f of x. So what we have is our y-intercept is equal to 3. So here's x and here's y. So we have 1, 2, 3, 4, 5. Okay, so here's 3. Then we have 1, 2, 3, 4, 5. Okay, so there's the 3. So we're starting at 3 and we have a slope of -1. So we want to go through this point here. Okay, so we have a line that looks like this basically. Okay, and we want to integrate from 0 to 5. So here's 0 and here's 5. So I'm going to draw little like dashed lines for the limits of integration. Okay, so we want basically this area under here, under the curve, and this area here. So we see how some of the curve is above and some of it's below. So we'll have to take that into account when we're finding the area. So the total of our integration is going to be integral from 0 to 5 of 3 minus x dx, okay? And this is going to be basically, so we're going to take this area, and because it's above, we're going to make that a positive. Okay, so we're going to make positive of, and the area of that is a triangle, right? So we have 1/2 times base times height, so that would be a 3 and another 3. So that's the first one. And then let's look at this second piece there. That falls below, so we have to put a negative sign in front, and then we just fill in the area in there. So that would be a 1/2 as well, because that's also a triangle. And then we have base times height, so that's a 2 and a 2. Okay, so let's just compute it here. So we have a positive 9 over 2, and then minus a 4 over 2. Okay, so what we're going to end up with is a 5 over 2. All right? Okay, so now let's go over some properties of the definite integral. So properties of the definite integral. Definite integral. All right, so we're going to start with the one that, let's say we have a graph, and we're going along, right, and we run into a graph that is constant. That means that it is at a constant height, right? Our y, the value of our function does not change. So that means if we integrate from a to b, and we take the area under this curve, right, from a to b, we're just going to get simply a rectangle, right? Because the bottom is then going to be the length b minus a, and then the height is always going to be a constant c. So that means that our integral from a to b of a constant function of a c dx is always going to equal c times b minus a. All right? So that's the constant function one. So this is if f of x is equal to c, which is a constant. All right? So that's an important relation to remember. And then we also have a couple more properties. So I'll write those on the next slide. So then we have what are called linearity properties, okay? So linearity and then properties. So we're going to start off by saying that if f and g, so if two functions are integrable, I think it's integrable, then we have over a certain interval, so over a, b, let's say, then we have two things. So number one, f plus g, so the addition or the sum of those two functions is integrable. I should look that up, the pronunciation, is integrable, and we have that the integral of that, so the integral of a to b of f of x plus g of x can be split up basically by this plus sign. So we have separately the integral from a to b of f of x dx, and then plus the integral from a to b of g of x, and then dx. Okay, so it's separated. It can be separated by that plus sign, and similarly for the with a minus sign as well. And then the second linearity property is that if c is a constant, if that's a constant, then we have that cf, so the constant times the function, is integrable. I'm just going to keep saying both pronunciations until I figure that out. And we have that the integral from a to b of c times f of x dx is equal to the integral of from a to b of f of x dx multiplied at the end by that c outside. So we can always move a constant outside, basically. Okay?
I just don't know what you will do.